Welcome back to our lecture series on automated machine learning, and we are in the age of foundation models. Now we would like to talk about how we can leverage large language models for AutoML. So let's directly dive into it. Overall, we're talking about automating algorithm design, which is already quite an old term, but now got new traction actually with the advent of large language models. The challenge is quite easy. Traditional algorithm design, we're doing it manually, for example, is labor intensive, require domain expertise, and is often done via a trial and error. The shift now, which we experience these days, is that we can leverage large language models because they possess capabilities beyond text generation. They can generate code or doing some kind of reasoning even. They can at least partially consider the semantic context of optimization problem. In all of that, we're aiming for to move from manual design to automated design via LLMs. And that should be obvious, is very close to the heart of automated machine learning, where we also always talk about manual design, which we would like to automate. The main idea behind all of that is that the LLM can function not only as an assistant, but as a core component in the algorithmic pipeline, maybe generating ideas, implementing code, acting as search operators. Here I will discuss with you a taxonomy which was proposed by Louis et al. In 2026. So the first idea is to see an LLM as an optimizer and simply saying that the LLM should iteratively refine a solution based on natural language feedback and the optimization history. So we're saying the input is the problem description. And we also have the history of solutions, very similar as we had that before. So, okay, we have different kind of designs or algorithms, and we already did an evaluation to that, knowing how good they are or not. And then we more prompt, of course, a bit more complex than I was written here, but more we prompting them to generate a better solution based on these past patterns and observations, in hopes that it will then output something new, which might be better. Limitations should be obvious to that approach, namely, it's very hard to interpret what's going on, why a new solution was really proposed, and a similar line of arguments, there's also no real theoretical guarantee behind that. Furthermore, these kind of systems are often very sensitive, for example, to the prompt use. So if I'm changing maybe slightly the wording of what needs to do, we're getting different results. Of the domain prior, so everything, for example, which is encoded also in the problem description, can make a big difference. And also the LLM itself. So if we're going, I don't know, from ChatGPT to Gemini, Claude, Qwen, DeepSeek, you name it, all of them might act quite differently because of different models. And also in relation then, for example, the LLM to the prompt, we've seen quite some sensitivity here. Furthermore, we can't ignore the computational cost with that approach, because we always have to think in terms of tokens. And the moment our history of solutions is growing over time, because we're generating new solutions, doing evaluation on them, and so on, that history will grow, and therefore also the input to our large language model is growing more and more, and therefore also token costs increases, which is not negligible in most cases. Furthermore, we can use LLM as a predictor, which means that we're using it more as a surrogate model as in Bayesian optimization to estimate the quality or behavior of a solution without really running the expensive evaluation to it. So first of all, of course, we can do the regression problem, which is then really, really close actually to Bayesian optimization. So for example, predicting a scalar fitness score, something like accuracy of a deep neural network. Or we can do classification, determining whether a solution is better or worse than a reference solution or the previous best one. Or we can also do zero-shot reasoning, so leveraging pre-trained knowledge to evaluate candidates where data is scarce actually. So for example, making more use of all these kind of task description and everything coming from maybe also external sources. Overall, what we're hoping to do is using the large language model with an input of our, let's say, configuration and some further context information, and that really acts as a replacement for our cost function we have normally. You already have seen in neural architecture search and scientific discovery that this can be quite efficient, especially for removing unpromising solutions. From my perspective, sometimes it has a harder task to really figure out what is the best one, but unpromising especially can be figured out quite nicely, which can save you a lot of time in practice. Then LLM can act as an extractor. So the LLM mines hidden features, constraints, or heuristics from unstructured problem descriptions to aid traditional algorithms. So for example, we have as an input some kind of unstructured text code, so optimize routing for fleet with limited fuel, for example, as doing some kind of semantic parsing and knowledge distillation based on that, and output some kind of structured artifacts, maybe in a JSON format, maybe some embedding, or maybe some problems features. Problems features, you should know, sometimes we call them beforehand meta features. And these give us information somehow about our problem. And if you're thinking about these kind of things, we can, of course, use them then to select, for example, the best optimizer or the best algorithm, the best whatsoever, whatever we would like to have, which is often then referred to as algorithm selection. Can be, of course, also used as a warm starting heuristic. So we identify based on this kind of information, meta features, and so on, what could be promising solutions, and then warm start any kind of optimizer set. LLM could also act as a designer, which means the LLM generates the algorithm itself, so code or function, rather than just a solution to a specific instance, which is also quite nice. So you can see it, for example, as that the LLM acts as a generator of a Bayesian optimization algorithm, and then using the very specific Bayesian optimization algorithm to solve our concrete problem. So it's more the designer of the meta solver on top of that. So the space is search within the program space, not the solution space now. Very important to note here. And could be, for example, used in an evolutionary algorithm driven by LLMs. So we initialize with some kind of seed program, doing some kind of mutation and crossover to write new codes, which is then acting as the program to solve the underlying task, doing some kind of evaluation and more checking how well is it doing. For example, how well is our new Bayesian optimization code doing on the given task, and then we selecting, keeping high performance code snippets and so on. So this is very typical EA approach, where the important really part is that mutation and crossover is done by the LLM. So we can here discover novel heuristics, for example, automated machine learning or Bayesian optimization, the different kind of approaches, how that can be done. And it has shown that we can outperform human designed baselines with that. The distinction lies in the output and the abstraction level. So to sum that a bit, these taxonomies in these kind of two things, right? So we had the optimizer. So the primary rule is to do directly the optimization. So the output is a solution instance. For example, if you're doing, I don't know, routing, then the route itself, the optimized one, should be the output. We can use it as a predictor. It's more as the output is the evaluation metric. So very concrete scores for certain solution candidates. Or we had the extractor, where the output is structured features, so some kind of knowledge about the problem or maybe about algorithms and so on. Or the designer, where we say the output is the executable program, for example, Python program, which encodes some kind of an optimizer, like Bayesian optimization algorithms, for example. Of course, you can combine all of these in different kind of ways. Often what people are doing right now is only doing one of these. because the LLM, of course, can fail if you're combining too much of these. The likelihood that one of these components at least is failing gets larger and larger. Nevertheless, there might be very nice opportunities for the future. So as a summary for all of that, we have seen a paradigm shift. So algorithm design is moving from purely analytic human tasks to a more semantic automated process driven by large language model. And we have this kind of hybrid intelligence nevertheless being involved, because now we can use Moore's LLM for reasoning, for suggesting new solutions. Some people also call that creativity. One can discuss that, how far that is really creative, but it proposes new things, and we can drive it in combination, for example, with classical evolutionary research to come up with better and better approaches. People are quite extensively exploring that direction right now. And it's more than just translating ideas to code. They really serve as a search operator and navigate the landscape of possible algorithms. And that makes it so powerful because in the past, for example, with genetic programming and so on, that was not super easy and often quite limited. Large language models seems to open up a new direction here, which means a self-evolving software system where the optimizer, predictor, and designer loops are fully autonomous. Challenges, as I already said, could be different kind of things. Furthermore, to be added here is code quality can be rather poor and hard to maintain, which can imply a very high technical debt later on. You have to be careful with that. At least as the beginning of 2026, I would call it more as technology to come up with first prototypes, not with production-ready code. Security can be a big issue. There are many, many papers and studies showing that this kind of generated code is not as secure as human-written code. And therefore, one has to be a bit careful with doing that. Nevertheless, I believe it's very promising what we can find there. And that will be part of the future of algorithm design. With that, I hope you have a new insights with that, a new understanding of what LLMs can do and what can they serve. And I hope you see us again in the upcoming videos.